So this question is concerned with looking at the transfer function of a state space model. So we know that the two state space equations are given by x dot equals ax plus bu and y equals cx plus du. First of all, explain the significance of a, b, c, d and vectors x, y and u. Right, so it's just asking us to explain what it all means, basically. It wants then a signal flow graph which maps input u to the output y, so it wants us to write down signal flow graph for the system. Then we're going to use Laplace in order to work out the transfer function ds for the system. So it wants to know for this state space system what is the transfer function, what is the output divided by the input, where output is going to be the y of s and the input is going to be u of s. And in fact, it's showing us, it's telling us what we want to get to, which is nice. From the expression then, we want to show that the poles of the transfer function correspond to the eigenvalues of the matrix Si minus A. So that's basically a nice proof of showing why it is that eigenvalues are the poles of the system. So let's go through this stage by stage. So a state space model, obviously it's a collection of first order ordinary differential equations which basically describes a system which can have high order overall, but we build it up from basically a row of separate first order equations. So we have x dot equals ax plus bu. So what are the terms here? Well, first of all, right, x dot is the time derivative, the first derivative of the state vector, and this is going to have elements in it. If we got three states, there would be three elements, and it's going to be a column vector. A is the system matrix, so this transforms basically the state part to or contributes to the derivative. X is going to be the state vector. Again, this is going to be a column vector with one element per state. B is going to be multiplied by the control input, so it's going to be the control input matrix, which tells us how the control input affects or contributes to x dot, and u is the control input itself. Right? So we've also got an output matrix equation, y equals cx plus du, so y is the output of the system. It can generally be a vector or a matrix. C is going to be the output matrix, so it tells us how the state x relates to the output. Although there is also a contribution there can be a direct contribution from the input. X then is the state vector again, which is going to be a column vector. And D is going to be the transmission matrix, so it's telling us how we can directly affect the output using the control input. And U is the control input. So that explains all the bits in the equations. So a state space model, of course, is given by x dot equals ax plus bu, y equals cx plus du. Obviously, this is the continuous version of state space models. You can also get discrete versions, but in this particular module, we're only concerned with looking at continuous time. We then want to write that down as a signal flow graph, and basically what you've got to do is just remember, I sort of would, if I was drawing this, I'd start off by writing down the x dot and the x. So x dot, this part of the equation here. First of all, to get to x from x dot, we need an integrator block. So we need to go through an integrator. So we integrate x dot, and we end up with x. And then the rest of it's just filling in the equation. So we can see x dot equals a times x plus b times u. So we need to tap off x, multiply it by a. So here we've got ax coming in here to this addition. And then we add that with u times b. So bu coming straight, the u input coming in, multiplied by b. So here we've got bu here, ax here. We add them together and that equals x dot. So that's the first equation sorted. Now we want to get the output, so the output's going to come out this end, and it's going to be the sum of cx and du. So we've got x here, so x has got to go through c, then we've got cx, and we're going to add that on to obviously du, so u comes in here, multiplied by d, and then we've got du. So here is cx plus du, and that gives us the output. Okay, so it's that simple. Now we want to map the state space model to a transfer function, right? So we've got our two equations, x dot equals ax plus bu, y equals cx plus du. Transfer function is then going to be the output divided by the input, remember? So it's going to be y divided by u in the S domain. So first of all, we need to get into the S domain. And since we're interested in transfer functions, we don't have to worry about initial conditions when we take the Laplace transforms. So just as we would for scalar or single variables or one-by-one matrices, you could always say as well, x dot goes to s, x of s, right? A is just a scaling matrix, x goes to x of s, b is a scaling again, b, and u goes to u of s. So that's easy for the first equation. Then all we need to do is collect up all the x of s terms together, right? So we collect them up. So if we take basically the ax of s away from both sides, we end up with sx of s take away ax of s, and then we factorise out the x. But we can't just factorise out and leave the s on its own, because basically it needs to multiply by the identity matrix in order to do that, because we're actually going to take this, we're going to have this, and we're going to take away the a from it. So this is the si means that this is basically, this is an element-wise multiplication of all the elements in here. So we can't just leave that on its own. It's got to be si in order to actually get the dimensionality correct, so we can actually take a away from it. Then we factor out the x. So we've got si minus a, xs equals bu. Next thing we want to do is we want to get xs onto the left-hand side, and we can't just divide through by si minus a because it's a matrix expression, but what we can do is we can multiply both sides by the inverse, and that way the inverse of this multiplied by itself basically goes to the identity, so we can forget about it, and then we've got the inverse appearing on the other side. So what we say is now xs equals s minus I a inverse of all of that times bu. Okay. Now we want to put in the expression for the output, because we've already got the expression for x, but we want to get rid basically of the intermediate things. So what we do is substitute now the expression for, so this is basically taking the Laplace transform of y equals cx plus du. So y goes to y of s, I should say, x goes to x of s, and u goes to u of s. So we now substitute this equation, right? We have this equation, and we substitute in what we just got for x of s into the term here for x of s, because we want to lose the x of s. We want an equation that's only got u in it and it's only got y in it, so we can calculate the transfer function. So we substitute basically this equation here, s I minus a to the minus 1 bu s. We put that in here, so we've got c multiplied by this lot plus du of s, right? Now again, we just have to collect up terms in u of s, because it's the ratio of y of s and u of s that we care about. So we collect up the terms, and we see we can factorise that out quite easily. We've got, this is the first term here, which is this bit here up to the u of s, and the d goes here. And then all we need to do is calculate y of s divided by u of s. So what we have to do is divide both sides by u of s. Right? And there we have the expression for the transfer function. Now, we're being asked to discuss the possibility of, well, you know, what do the poles and the eigenvalues, you know, how are they related? How are these things related? So what we're going to do is we're actually going to expand out this inverse, right? We've got an inverse matrix here, right? S minus AI, we calculate the inverse. So what is the inverse? How do we generally calculate the inverse of a matrix? And there's generally there's two things we have to do in order to calculate the inverse of a matrix. We have to rearrange the bits in there. If it was 2 by 2, we just swap over A and D, and we change the signs of B and C. In general, we call that, it's going to be the adjunct of the matrix. So if this is bigger than 2 by 2, it's a bit more to it than that. But the expression for this switching around of the orders and stuff is calculating the adjunct matrix. And the other thing we have to do after we switch the things round is we have to divide by the determinant of the matrix. So we can just say det of Si minus A. Right? So doing the adjunct and dividing it by the determinant will calculate the inverse if it is basically in existence, right? So we just basically substitute in what we need to do to calculate the inverse into the equation here. And now we can look at this equation, and when do we have poles of transfer functions? Well, we have poles of transfer functions when the transfer function goes to infinity, if you recall, and we get infinity when we divide by 0. So we're going to get a pole when this denominator term goes to 0. So what this is saying is when the determinant of Si minus A goes to 0, then we've got a pole. So that's the equation, determinant of Si minus A, right? But, right, that expression gives us the eigenvalues of this matrix, right? So S is going to be the eigenvalue of this matrix, the solution to this problem. Therefore, we get a pole at the eigenvalues, and that's why poles and eigenvalues are related in this way.